Caution: this video is for educational purposes only. We assume no liability for injuries or damage caused by imitating the experiment. Please observe the legal regulations that apply to you when handling chemicals. Today we show the preparation of elemental bromine using sodium persulfate as the oxidant. This method has several advantages. There are no interhalogen compounds, no hydrogen bromide and no sulfuric acid aerosols that can contaminate the target product. No waste containing heavy metals is produced, just harmless sodium and potassium sulfate. Also, sodium persulfate is more readily available and cheaper than other oxidizing agents. Finally, this method also enables high yields of over 90% if fresh sodium persulfate is used. But more on that later. Before we start, it should be emphasized that experiments with elemental bromine should only be carried out under a fume hood or outdoors, due to its highly toxic and corrosive properties, and that appropriate personal protective equipment should be used. Bromine can easily kill you if mishandled, so this experiment is not for beginners. As you can see, we set up a simple distillation apparatus for the synthesis. Since bromine destroys plastic and cork, you have to work with a pure glass grinding apparatus. The glass joints must be lubricated with a high temperature resistant Teflon paste, as other ground glass greases are attacked by bromine. We also use ground clamps for more stability and safety. In a 100 ml round bottom flask, place 50 grams each of potassium bromide and sodium persulfate. Mix and add 150 ml of distilled water. It is not necessary for the salts to completely dissolve in the water. The flask is heated using a silicone oil bath placed on a hot plate. Magnetic stirring is optional, adding boiling stones and temperature control are not required. The immediate yellowing of the mixture indicates that small amounts of bromine form even when cold. The bromine condensate is collected in a 100 ml flask, which is chilled in an ice water bath to minimize losses due to the bromine evaporation even at mild ambient temperatures. Any vapors that do escape are diverted via the still head to an inverted funnel trap in an alkaline sodium sulfite solution, where they are completely neutralized. Strong evolution of bromine vapors occurs during the heating of the reaction mixture. These form liquid bromine in the Liebeck condenser. The element flows into the template at a high drip rate, so that the reaction is complete after about 15 minutes and is therefore over. The end of the reaction can also be recognized by the fact that the gas phase in the reaction flask is clearly brighter and instead of bromine, water vapor is produced, which condenses in the cooler and floats in the receiver as water droplets on the bromine, which has more than 3 times the density. The salt layer that has formed in the reaction flask consists of sodium and potassium sulfate and traces of bromine, which are neutralized with sodium sulfite so that the mixture can then be safely flushed down the drain. In a last step, in which a gas mask should be worn at the latest, the bromine is transferred from the template into a separatory funnel. The bottom layer is nearly pure bromine, which is drained into another flask. The upper layer consists of small amounts of bromine water, which can either be stored and reused or neutralized and disposed of. We now have our end product in the glass stoppered flask, about 8 ml or about 25 grams of elemental bromine. This corresponds to a yield of 74% compared to the theoretical possible value. This is a low yield compared to previous runs we made. As already mentioned, yields of 90% and more can normally be achieved with this method when relatively fresh persulfate is used. Unfortunately, this last delivery was not of such good quality. The crystals were clumped and weathered, so that a certain proportion must have already decomposed into sodium sulfate and oxygen. For this reason, sodium persulfate should be stored in a cool, dry, dark place and only in containers with pressure equalization valve. Otherwise, the container could burst due to the pressure of the oxygen gas released. Thanks for watching. Be back for next Sunday's video. If you liked today's video, please subscribe to our channel. Ratings and comments are welcome too. If you'd like to see a specific experiment, post it in the comments and we'll see what we can do.